Chemical reactions. So a chemical reaction is a chemical change, and we've talked about chemical changes. In a chemical change, the original substance gets destroyed, and we make a new substance. But the atoms themselves are not destroyed. The molecules can come apart into individual atoms. The atoms can be recombined into new molecules, but the atoms themselves are still there. It's like building with Legos. You got this Lego set, and it's, Harry Potter's castle or something. And you take that apart and you build some other things. You have the same Lego bricks that you had at the beginning. It just looks different because you're putting them together in different combinations. But the mass is unchanged. That's part of why the law of conservation of mass works. Because in a chemical reaction, we're not destroying any of the atoms, we're just rearranging them. So a chemical equation is a shorthand way of describing a chemical reaction instead of a very long, tedious sentence. The general idea here is that we have reactants, the things that react, and an arrow pointing in the direction that this thing is going to happen, and then the products. So the reactants react to produce the products. In an equation, we're going to have the formulas for the reactants and products. We will often have their states, the physical states, and we will have the relative numbers of molecules of reactants and products. And so this can be used to predict how much iron we're going to get from this particular iron ore, this compound containing iron. We'll do a process, a chemical reaction. How much iron can we get out of it? So very useful sort of information. These are the state symbols. We usually call them state symbols that we use. Oops, that was the wrong button. G for gas, L for liquid, S for solid. AQ means aqueous, dissolved in water. So let's look at a reaction, the combustion of methane. So we can describe this as in a sentence. Methane gas burns to produce carbon dioxide gas and gaseous water. Anytime something burns, oxygen is necessary. So if they're telling you that, this thing is burning, and they only give you the thing, they say, well, write an equation for the combustion of ethanol. And they give you the formula. Like, well, is that all? Well, the other thing is oxygen. Anytime you have combustion, oxygen is a reactant. So we can take those words and convert them into formulas. We'll learn in a few minutes how to take methane and make CH4 out of that. Here's CH4. To burn means we have oxygen. The formula is O2 here because oxygen's a diatomic element, and here it's not part of a compound, it's by itself. So the oxygen atoms do not want to be out alone, right? So they're going to go out in pairs. And then the products, so to produce, that's our arrow, carbon dioxide, gas, and plus water in the gas state. Okay? If we look at this, though, there's a problem. Because over here we have 2 oxygen atoms, and in the products there's 2 oxygen atoms here, and there's another one over there. And so it looks like we've created an oxygen atom. Can we do that? Nope, can't do that. There's also a problem with the hydrogens. On the left, there are 4 hydrogen atoms, and in the product side, there's only 2. Well, maybe those 2 missing hydrogens turned into an oxygen. That would solve the problem. Could that happen? Nope, not. There's just some things missing from our chemical equation. We don't have the right ratios, the right numbers of molecules. So this violates the law of conservation of mass, and we can't have that. So here we have that same equation, but now we're putting coefficients in here. Here, you could think of these as round Legos. So here we have a methane molecule and 2 oxygen molecules. And what we need to be able to do is take these things apart, put them back together, and make these things. And if you count up the red balls and the white balls and the black balls, you can do it. If you're missing one of these, it's not going to work. If you're missing one of those, it's not going to work. You can't have leftover pieces. So we figure out how many of each of these molecules we need so that we could take what we've got, break it apart, make the new thing. So we put a 2 in front of O2 to tell us we need 2 of these units. And then we're going to make 2 water molecules, so there's a 2 there. We can count up the elements on each side. We look at the CH4, there's 1 carbon atom there. H4 tells me there's 4 hydrogens, and 2 O2 units, there's 4 oxygen atoms. On the right side, there's 1 carbon, and the hydrogens are over here now, but there's 2 water molecules. They each have 2 hydrogens. 2 times 2 is 4 hydrogens. And I've got 2 oxygens here and 2 oxygens there, 4 oxygens. So if I look at the total number of atoms of carbon, atoms of hydrogen, atoms of oxygen, it's the same before and after. That's what we're doing when we balance chemical equations. Okay? So these are sort of guidelines for balancing chemical equations. I can't give you a list that will always work beautifully. We call this balancing by inspection, and it's kind of a trial and error process. You do need to start with something, right? You need to start with a skeletal equation that contains the formulas for the reactants and the products. And those formulas need to be correct. Okay? So you got to start out with the correct formulas. Then this part in the middle is kind of up to you. Suggestion is to balance atoms that are in more complex substances first, always balancing the things that are in compounds before atoms in the pure elements. Anything that occurs as a free element, that would be a good idea to leave that one until last. Because when you stick a coefficient in front of O2, it only changes the oxygens. It doesn't change the hydrogen or the carbon. And if you leave something complicated to the end and you change the coefficient, then you mess up everything else. Sometimes when you're balancing things, you might find yourself using fractions for coefficients. That is absolutely fine. But when we finish our equation, we want to get rid of those fractions, multiplying by the denominator of the fraction. I'm not going to demonstrate fractions because if you're good with them, you don't need that. And then you should always check your work at the end. So those are the guidelines. Let's do a couple examples, and we'll get some review of nomenclature in here. Write a balanced equation for the reaction between solid silicon dioxide and solid carbon to produce solid silicon carbide and carbon dioxide gas. So we're taking a sentence and we're making it into a chemical equation. So the word and means plus. To produce, that's where the arrow is. And there's another and here, and that's going to be plus. So we've got silicon dioxide plus carbon, arrow, silicon carbide plus carbon monoxide. Well, silicon dioxide. What's the formula for that? SiO2. That is a molecular compound because silicon and oxygen are both on the nonmetal side of that line on the periodic table. We are told it's a solid, so I'll put S in parentheses after the formula. So it's that and plus solid carbon. It's just an element, C, and then ask yourself, is it one of the 7 diatomic elements? Horses need oats for clear brown eyes. Nope, it's not one of those. So it's just carbon by itself and solid. And then my arrow leave some space before the chemical formulas because you might need to put a coefficient in there. My products, the first one is silicon carbide. Well, would that be a molecular or ionic? Silicon is on the non-metal side, right? It's a semi-metal, but if it's on the non-metal side, it gets treated as a non-metal for nomenclature. So this is going to be a molecular compound. It doesn't have any prefixes in it, right? That's kind of disturbing. How do I know? Well, what's the one that we omit all the time? Mono. So in this one, we've omitted the mono on the first one and the mono on the second one. Don't ask me why, they just did. So this is SiC. I used to be able to ask Siri what the formula for silicon carbide was, and she'd tell me it's SiC. She doesn't do that anymore. She gives me way too much information. It's no fun. Silicon carbide, solid. Plus carbon monoxide. It's a gas, CO. It's a capital O. It's not cobalt. So we got our skeleton in here. And now we're going to inspect it. We're just going to look at it. We have carbon all by itself here, so that's probably going to be saved for last. Many times, if you just start with the first element, it works out fine. So I'm going to do silicon first. There's one silicon on the left side of the arrow. There's one silicon on the right side of the arrow. So far, so good. Here's oxygen. There's two oxygens here, and on the right side, I only have one oxygen. The oxygen is only in the CO, so I could make two oxygens by putting a 2 in front of the CO. You can't make it into CO2 because that's not carbon monoxide. You can't change the formulas. You can just put numbers in front of the formulas. So now I've got two oxygens. When I put this 2 here, did it mess up the silicon? No, it didn't affect the silicon at all. Okay, so we've got the first 2 done. Now we're going to look for carbon. I've got one carbon here, and you have to look everywhere. There's a carbon hiding right here, and then in the carbon monoxide, I've got how many? 2. So I have a total of 3 carbons on the right side. So then I need to put a 3 in front of the carbon over there. And when I did that, it didn't mess up the oxygens or the silicons. And there's the balanced equation. Any questions? That was an easy one. Write a balanced equation for the combustion of gaseous ethane, C2H6, a minority component of natural gas, in which it combines with gaseous oxygen to form gaseous carbon dioxide and gaseous water. So here, combines with, right, so that's plus, to form this and that. Well, I'm given the formula for ethane, C2H6, and I'm told it's a gas. It's reacting with oxygen. What's the formula for oxygen? O2. It's a diatomic element. This is where we need to use the diatomic elements, when they are elements by themselves. Hydrogen is a diatomic element, but I don't need to put a 2 on it here because it's with other hydrogen and carbon atoms. It's fine. To form, so we've got carbon dioxide this time, CO2, again, it's a gas, and gaseous water. So water's H2O, and I'm going to put a G there. Why is this not liquid water? Is this natural gas burning? Is it at room temperature? No, it's hot, right? It's hot. So that's why the water's in the gas thing. Okay, I'm going to show you what I call the tally method for balancing chemical equations. And use it if you like it, and if you don't, then don't. So I'm going to draw a line down the middle because I'm balancing on each side of the arrow. And then I'm going to take some inventory. I'm going to list the different kinds of elements I've got. I've got carbons, I've got hydrogens, and I've got oxygens. And then I'm going to go across and look at each compound or element and write down the number of atoms that I have there. So for C2H6, I have 2 carbons, and there are 6 hydrogens, and there are no oxygens. The zeros tend to look like O's and get all messy, so I just do a dash. Over here, O2, well, that's 2 oxygens. There's no hydrogens, no carbons. CO2 has 1 carbon, no hydrogens, 2 oxygens. H2O, no carbons, 2 hydrogens, 1 oxygen. So we've got these same 3 elements, and they're all jumbled up, right? So I took inventory. Now I'm going to look, and it often works out just, start with the first one. Look at carbon. Well, I've got 2 carbons, 2 plus blank, and over here I have 1 plus blank. So I need to multiply this to get 2. Well, that's not too hard. It's not too hard to get 2 by multiplying by 2. Sorry. Multiply that by 2. So when I put a 2 in front of CO2, it changes everything. So all of those numbers underneath, I have to multiply by 2. So this becomes 4. My carbons are balanced. Then I'll look at my hydrogens. I have 6 hydrogens on the left and 2 on the right. How do I make a 2 into a 6? Multiply by 3. So I put a 3 in front of H2O, and then I have to multiply all the numbers underneath it by 3. So this becomes 6, and this becomes 3. I didn't mess up the carbons, so that's okay. Carbon and hydrogen are both balanced, and now I can look at the oxygens. I've got 2 oxygens here, and I have 4 plus 3 is 7. Yeah, question?
I wanted to ask if my solution was correct, but I don't know. That might be jumping the gun for you to explain.
Yeah, why don't you wait and see?
Okay.
So here we've got 2, and here 4 plus 3 is 7. I need 7 oxygens on the reactant side. Yeah, I could do 7 halves. So if that makes sense to you, you're fine. I'm not going to explain that. Some of you are like, oh, I hate fractions. It's the F word, right? No fractions. Okay, well, I have an even number here and an odd number there. This is the odd-even problem. It's like if you want 7 shoes, not 7 pairs of shoes, 7 shoes, how many pairs do you need without any extras? Well, you can't really do that, right? You need like 3.5. You can't have half of an O2 molecule. How do you make an odd number into an even number? Multiply by 2. So if I multiply all of this that I've done by 2, then my odd number goes away. And if you're doing it the fraction way, you're going to end up doing this anyway. So I'm going to multiply this by 2. That's going to give me a 6. This is going to be 12. This is going to be 6. I'm going to multiply this one by 2, so I've got 4. That's going to become 4. This will become 8. I haven't done anything to this one yet. I need to multiply this one by 2, so that becomes 4 and 12. When I doubled everything, I did not mess up the carbon and hydrogen balance. I just have twice as much on both sides. Now when I look at the oxygens that I need, I've got 8 plus 6 is 14. And over here I've got 2. If I put a 7 in front of that, I could get 14 oxygens. Put a 7 here, multiplies that, I get 14. And now 8 plus 6 is 14. And it's all balanced. That is not the only way to balance that equation. But this is the correct equation describing this chemical reaction. We want to have the lowest whole number coefficients. Okay? Sometimes you go around in circles a few times and you might end up with 4, 14, 8, and 12. Well, is it balanced? Yes. Is it the best correct equation? No, because you could divide all of those by 2. So did your method work?
Yes.
It worked? Cool. Anybody have any questions? Sometimes you start balancing an equation and you find that you're like going around in circles because, if I change this, then that changes the carbon and the oxygen, and then I end up going over here to change this to fix the carbon, and that changes the hydrogen. I go over here and I change it, and I'm going around in circles. If you recognize, oh wait, I've gone around this tree twice, just stop. It's not going to get any better. Often what's happened is that one of your equations, one of your formulas is not correct. If you have an incorrect formula, it's just not going to work. So check your formulas, and if they're correct, then start over with a different element. Some elements are easier to start with than others, and that you can't always predict. Question? Well, we can't balance ions in here because there aren't any ions. But the next one has ions. Any questions about this one? I don't know if it said this in the book. Anytime you have a combustion with carbon, hydrogen, it may or may not have oxygen. The products are always the same. It'll be CO2 and H2O. Okay, let's do one with ionic compounds. Write a balanced chemical equation for the reaction between aqueous lead-2 nitrate, aqueous potassium chloride to form solid lead-2 chloride, and aqueous potassium nitrate. We need to write formulas for these ionic compounds. So I'm just going to look at this first one, lead-2 nitrate. Now, lead is Pb, and the Roman numeral 2 tells me the charge, 2 plus. What's the formula for nitrate? It's NO3 minus. So I look at the charges, and that tells me I need 2 nitrates for the 1 Pb. So then that one, my first reactant is Pb, NO3, 2. I'm told it's aqueous, so I put AQ in parentheses. Plus, I've got another aqueous one, potassium chloride. Potassium's a metal, so this is also ionic. Potassium is in group 1A, so it's got a +1 charge. Chloride is a Cl minus. Those charges are opposite but equal, so I just have KCl, and that's also aqueous. To form is my arrow. Lead-2 chloride, that's the lead-2 from this one and the chloride from this one. So I need 2 of the chlorides to go with lead-2, PbCl2, and I'm told that's a solid. I don't put parentheses around the chlorine because it's not a polyatomic ion. And aqueous potassium nitrate. So there's potassium and nitrate. +1 and -1, I just need 1 of each. KNO3. And I don't use parentheses there because I only have 1 of the polyatomic ion. And that one's aqueous. So that's all nomenclature stuff. There is nitrate ion in the reactants, and there's nitrate ion in the products. Much of the time, polyatomic ions remain intact. So you can balance the individual elements, nitrogen and oxygen, or you can balance NO3 as a unit. Okay? So I'm looking at this and I'm seeing that, well, I have 2 nitrates here, and over there I only have 1 nitrate. So I could put a coefficient of 2 in front of the formula, and that would give me 2 nitrates, or 2 nitrogens and 6 oxygens. There's 1 Pb here and 1 Pb there. Here I have 2 chlorines, and over here I only have 1 chlorine. So I need to put a 2 in front of KCl. And then now I have 2 Ks, and over there I've got 2 Ks, 2 potassiums. And so it balances. So I kind of went back and forth across, and you don't want to end up missing anything. So when you think you're all done, go back and check. Lead, got 1 and 1, that's good. Here's nitrate, there's 2 of them. Okay, 2 nitrates over there. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines. Good. Any questions? This is another thing that takes practice.